can be used to check the efficiency of heat engine. Next, TS diagram can be used to obtain the TS diagram can be used to obtain the work value of the fuel used. Next, TS diagram is used. TS diagram is used in metrology. TS diagram is used in metrology. So these are the four uses we are using in TS diagram. These are we are using in four uses in TS diagram. Nothing but these are uses of TS diagram. Is it clear? So in this lesson, what we discussed, work done in isothermal process, work done in adiabatic process. Work done in isothermal process means W is equal to 2.3026 RT log 10 V2 by V1. Work done in adiabatic process means W is equal to R by 1 minus gamma T2 minus T1. Now, and then what we discussed, efficiency of heat engine, entropy of the system, change in entropy, and entropy disorder, change of entropy when I change into stream. That all we studied in this. That all we studied in this particular lesson clearly. Okay. S2 minus S1 is equal to integration of dq by d, and entropy S is equal to K into log E of W. Change in entropy of the system means S2 minus S1 integral dq by T, and entropy of the system means Q by T is equal to S. Efficiency of the heat engine is eta is equal to 1 minus T2 by T1, and thermodynamic scale of temperature or Kelvin scale of temperature is Q1 by Q2 is equal to T1 by T2. Next, second law of thermodynamics is dq is equal to TdS. And first law of thermodynamics is dq is equal to du plus dw. All these we are studying in this particular lesson. Next, based on that the reversible, irreversible engine and efficiency, we can study the problems also. We did problems also. Next, first law of thermodynamics, Maxwell's potentials also we completed. Again, we recap that what is first one is internal energy, and second one is in Helmholtz function, third one is enthalpy, and fourth one is Gibbs function. So Maxwell's equations, simply recap, already over these are. What it is, Maxwell's, here we can take the first law of thermodynamics, dq is equal to du plus dw, dq is equal to du plus pdv. According to second law of thermodynamics, dq is equal to TdS. You are substituting these two in above equations. What it is, TdS is equal to du plus pdv. Then du is equal to TdS minus pdv, which is equation number 3. Now the above relations are not sufficient to explain the complete behavior of the system. The above relations are not sufficient to explain the complete behavior of the system. For the complete description of the system, certain other relations are for the complete description of the system. Certain other relations are required. For this purpose, we used certain for this purpose we used certain energy terms are some functions of variables. Pressure P, volume B, temperature T. Pressure P, volume B, temperature T, and entropy S are known as thermodynamic potentials. Keeping any two variables independent in the equation 3. Keeping any two variables is independent in equation 3. The other two variables can be determined. The other three variables can be determined by using above equations. Therefore, these are called as thermodynamic potentials. The state functions that along with the corresponding equations, the state functions that along with the corresponding, the state functions that along the corresponding equations of the state describes the equilibrium behavior of the system. Equilibrium behavior of system as the function of the norm, as the function of the natural variables. As the function of the natural variables are called thermodynamic potentials. Thermodynamic potentials are energy functions. Thermodynamic potentials are energy functions. Thermodynamic potentials are energy functions formed by combining the basic thermodynamic variables. There are four thermodynamic potentials. One is internal energy, Helmholtz function, enthalpy or total heat function. Next, fourth one is Gibbs function. Next, internal energy. What is internal energy? U, the sum of kinetic energy of the molecules. The sum of kinetic energy of the molecules of the gas as and potential energy possessed by the potential energy possessed by the intermolecular introduction constitution is called internal energy. It is denoted by U. Therefore, U is equal to UKE plus UPV. U is equal to UKE plus UPV. Okay, internal energy is the state function. Internal energy is the state function. It depends only on initial and final states of the system. It depends only on the initial and final states of the system. It depends only on initial and final states of the system. The change in internal energy does not depend on the path followed. The change in internal energy does not depend upon the path followed. According to first law of thermodynamics, dq is equal to du plus du plus dw. dq is equal to du plus what is dw ma pdv. Then du is equal to what we are taking, dq minus du is equal to dq minus pdv. Then du is equal to what is dq tds minus pdv, which is equation number 1. Hence u is the function of entropy. U is the function of entropy and volume. U is the function of entropy and volume. U is equal to f of sp or u comma sp. Next, it gives heat content at constant volume. Next, Helmholtz function F or Helmholtz free energy F. The thermodynamic property of a system, which is equal to the difference between the thermodynamic property of a system, which is equal to the difference between its internal energy and the product of its entropy. And the product of its entropy and temperature is called, and the product of its temperature, entropy and temperature is Helmholtz function. It is denoted by F. It is denoted by F. F is equal to U minus Ts. F is equal to U minus Ts. Then dF is equal to du minus Ts. dF is equal to du minus Tds minus SDT. Differentiating the equation, what we are getting, ma? dF is equal to Tds minus Pdv minus Tds minus SDT. Then dF is equal to plus TDS minus TDS gets cancelled. We have to take dF is equal to minus PdV minus SDT, which is equation number minus PdV minus SDT, which is equation number 2. Okay. Hence, F is the function of volume and temperature. F is the function of volume and temperature. Therefore, F is equal to F of P comma T. Next one, enthalpy or total heat function. Enthalpy or total heat function. the extensive thermodynamic quantity, equivalent to total heat content of a system. The extensive thermodynamic quantity equivalent to total heat content of a system is called enthalpy. It is denoted by H. Therefore, H is equal to U plus PV. H is equal to U plus PV. dH is equal to du plus PdV, du plus PdV plus VdP. Therefore, dH is equal to, what is du ma? TdS minus PdV plus PdV plus VdP. Then plus PdV minus PdV cancel. We have to take dH is equal to TdS plus VdP, which is equation number 3. Therefore, enthalpy is a function of entropy and pressure. Therefore, H is equal to F of S comma P. It gives the heat content at constant. It gives the heat content at constant pressure. Next one, Gibbs function. What is Gibbs function, ma? It is denoted by the letter G, the thermodynamic property of a system. The thermodynamic property of a system, which is equal to the difference between its enthalpy and the product of entropy. Its enthalpy and the product of entropy and temperature is called Gibbs function. Its product of enthalpy, entropy and temperature is called Gibbs function. It is denoted by G. Therefore, G is equal to H minus T. G is equal to H minus Ts. dg is equal to dH minus TdS. dg is equal to dH minus TdS minus SdT. dg is equal to dH minus TdS minus SdT. Then dg is equal to TdS plus VdP minus TdS minus SdT. Then here also we cancel plus TdS minus TdS. Then you have to take dg is equal to VdP. dg is equal to VdP minus SdT, which is equation number 4. Therefore, hence G is a function of pressure and temperature. Therefore, G is equal to function of pressure, comma T. Next one, Maxwell's thermodynamic relations or Maxwell's equations. Now, thermodynamic equations are Maxwell's equations. From thermodynamic potential, a thermodynamic system may be described. Thermodynamic system may be described fully. Thermodynamic system may be described fully. Thermodynamic system may be described fully in terms of thermodynamic variables. Pressure P, volume V, and temperature. Pressure P, volume V, and temperature T, and entropy S. Maxwell deduced important relations by using laws of thermodynamics. Maxwell deduced important relations by using laws of thermodynamics called Maxwell's thermodynamic relations. From the thermodynamic variables, and two can be chosen. From the thermodynamic variables, and two can be chosen independently, and other can be determined in terms of chosen quantities. First Maxwell equation. According to equation of change in internal energy of a system, according to equation of internal energy of a system, dq is equal to du plus dw, du is equal to dq minus dw. Then du is equal to what is dq ma? TdS. What is dw? PdV. Therefore, du is equal to TdS minus PdV, which is equation number 1. But we know that internal energy is a function of internal energy is a function of entropy and volume. Therefore, U is equal to function of S comma V. Next, du is equal to du by ds of V comma ds plus dou by dou V of S into dou V, which is equation number 2. Now comparing equations 1 and 2. Dou U by dou S of V is equal to T and dou U by dou V of S is equal to minus P. Dou U by dou V of S is equal to minus P, which is equation number 3. Therefore, as the change in internal energy, du is perfect differential. As the change in internal energy, du is perfect differentiation. As the change in internal energy, du is perfect differential. Therefore, dou by dou V of dou U by dou S of V, dou U by dou V of dou U by dou S by dou by dou S of dou U by dou V. Therefore, substituting equation 3 in equation 4. What it is, ma'am? Dou by dou V of dou U by dou S of V. Dou by dou V of dou U by dou S of V is equal to dou by dou S of dou U by dou V of S, which is equation number 4. Therefore, substitute equation 3 in equation 4. Equation 3 ni equation 4 లో సబ్స్టిట్యూట్ చేస్తే ఏమొస్తుంది మేడం మనకి? మ్యాక్స్వెల్స్ ఫస్ట్ ఈక్వేషన్. అప్పుడు ఏమవుతుంది? డో టీ బై డో వి ఆఫ్ ఎస్ ఇస్ ఈక్వల్ టు మైనస్ డో పీ బై డో ఎస్ ఆఫ్ టీ అవుతుంది. దాన్ని మనము ఫస్ట్ మ్యాక్స్వెల్ ఈక్వేషన్ అంటాము. దిస్ ఈక్వేషన్ ఇస్ నోన్ యాజ్ ఫస్ట్ మ్యాక్స్వెల్ ఈక్వేషన్. Similarly, we are getting from second potential to second Maxwell equation. According to equation of change in Helmholtz function. According to equation of change in Helmholtz function. DF is equal to, according to equation of change in Helmholtz function, DF is equal to minus PdV minus SdT. But we know that Helmholtz function is a function of temperature and volume. Therefore, F is equal to F of T comma V. Capital F is equal to function of T comma V. Therefore, DF is equal to dF by dt at constant volume into dt. dF by dt at constant volume into dt plus dou F by dou V at constant volume dou V into T, which is equation number 6. Now comparing equations 5 and 6, we are getting the final equation. Now, what it is, my dou F by dou T of V is equal to dou F by dou T of V is equal to minus S, and dou F by dou V of T is equal to minus P, which is equation number 7. That we are substituting in above equation with as the change in Helmholtz function. DF is perfect differentiation. As the change in Helmholtz function, DF is perfect differential. Therefore, dou by dou V of dou F by dou F dou by dou V of dou F by dou by dou V of dou F by dou T of V is equal to dou by dou T of dou F by dou V into T, which is equation number 8. Therefore, substitute equation 7. Substitute equation 7 in equation 8. Then minus dou by dou V minus dou S by dou V of T is equal to minus dou P by dou T minus dou P by dou T of V. Minus dou S by dou T of V is equal to minus dou P by dou T of V, which my both sides minus gets cancelled. Then what it is, ma? Dou S by dou V of T. Dou S by dou V of T is equal to dou P by dou T of V, which is Maxwell's second equation. Next, third Maxwell equation. According to the equation of change in enthalpy, according to the equation of change in enthalpy of a system, dH is equal to TdS plus VdP. Equation 9. Now we know that enthalpy is a function of, entropy and pressure. Therefore, H is equal to F of S comma P. Dou H is equal to dou H by dou S of P into dou S plus dou H by dou P of S into dou P, which is equation number 10. On comparing equations 9 and 10, what we are getting, dou H by dou S of P is equal to T, dou H by dou S of P is equal to T, and dou H by dou P of S is equal to B. Dou H by dou S of P is equal to T, and dou H by dou P of S is equal to B. That is 11. Therefore, as the change in enthalpy, dH is a perfect differential. As the change in enthalpy, dH is a perfect differential. Dou by dou P of dou H by dou S of P is equal to same way. All three equations, all four equations, we are following same procedure, but the functions are different. So here what we are taking, dou H by dou S of P is equal to T, and dou H by dou P of S is equal to B. This 11th equation now we are substituting in 10th. Then we are getting dou by dou P of dou H by dou S of P is equal to dou by dou S of dou H by dou P of S. Equation 12. Substitute 11th equation in 12. Then instead of dou H by dou S of P is equal to what we are taking, dou H by dou S of P. Change in enthalpy dH is a perfect differential. Then differentiating that means dou by dou P of dou H by dou S of P is equal to dou by dou S of dou H by dou P of PS. Then substitute 11 in 12. Then dou T by dou P of S is equal to dou V by dou S of P, which is equation number 3. Therefore, the above equation 3 shows the third Maxwell equation. Above equation 3 shows the third Maxwell equation. Next, fourth Maxwell equation. According to equation of change in Gibbs function, dz is equal to bdp minus bdp minus sdt. But we know that g is a function of pressure and temperature. G is equal to function of pressure and temperature means here what we are taking, dou g is equal to dou g by dou p of t comma dp plus dou g by dou p of p comma dou t, which is equation number 14. On comparing above equations 13 and 14, we are getting the equation is dou g is equal to dou g by dou p of t dou p plus dou g by dou t of p dou t. Now comparing 13 and 14 equations, we are getting dou g by dou p of t is equal to volume, dou g by dou t of p is equal to minus s. Now above equation becomes dou by dou t of dou g by dou p of t is equal to dou by dou p of dou g by dou t of p, which is equation number 16. Now substitute 15 equation, 16th equation. We are getting dou v by dou t of p is equal to minus dou s by dou p of t, which is Maxwell's fourth equation. Okay, Maxwell's fourth equation. So final, totally we have to take four equations. Next one, classes Clapeyron equation. Here also same. Already we derived that dou p by dou t is equal to L by T into V2 minus V1. L by T into V2 minus V1 is the Clapeyron equation. Dou p by dou t is equal to L by T into V2 minus V1. So next, specific heat at constant pressure at constant volume, and relation between them is Cp minus Cv is equal to R, and ratio of between them is Cp by Cv is equal to, relation between them is Cp minus Cv is equal to gamma. Ratio between them is Cp by Cv is equal to gamma. Okay, ma. Next, Joule Kelvin effect or Joule Thomson cooling. Joule Kelvin effect or Joule Thomson cooling. Very, very important topic. Joule Kelvin effect or Joule Thomson cooling ma. Joule Kelvin effect or Joule Thomson effect, what it shows ma, when a gas is passed through porous plug, when a gas is passed through porous plug from a constant high pressure region to a constant low pressure region, when a gas is passed through a porous plug from a constant high pressure region to a constant low pressure region, there is a change in its temperature. This phenomenon, there is a change in its temperature. This phenomenon is called as Joule Kelvin or Joule Thomson effect. This phenomenon is called Joule Kelvin or Joule Thomson effect. When a gas is passed through a porous plug from a constant high pressure region to a constant low pressure region, there is a change in its temperature. This phenomenon is called as Joule Kelvin or Joule Thomson effect. At ordinary temperatures, all gases except hydrogen and helium, ordinary temperatures, all gases except hydrogen and helium suffers a fall in temperature. While hydrogen and helium suffer a rise in temperature in Joule Kelvin effect. The change in temperature is directly proportional to the pressure difference on the two sides of the porous plug. The change in temperature is directly proportional to the pressure difference so that inversion temperature, the change in temperature is directly proportional to the pressure difference on the two sides of the porous plug. It means dt is directly proportional to dp. In Joule Kelvin effect, total enthalpy of a gas is constant. Inversion temperature Ti. A certain initial temperature at which the cooling effect is changed into heating effect. Is known as inversion temperature. It is denoted by Ti. Now Joule Kelvin coefficient mu Jt. When a gas suffers Joule Kelvin effect, the total enthalpy of the gas. When a gas suffers Joule Kelvin effect, the total enthalpy of the gas remains constant. Therefore, H is equal to constant. U plus Pv is equal to constant. Differentiation of U plus Pv is equal to 0. Then du plus pdv plus vdp. Is equal to 0, which is equation number 1. Now, according to first law of thermodynamics, what it is, ma? dq is equal to du plus dw. According to first law of thermodynamics, dq is equal to du plus dw. du plus dw. Then dw means pdv. Then according to second law of thermodynamics, dq is equal to tds. From second and third equations, what we are taking, tds is equal to du plus pdv. That is fourth equation. Substitute fourth in 1. Then what it is, ma? tds plus vdp is equal to 0. TDS plus VDP is equal to 0. Du plus PdV plus we are substituting TdS. Then above equation 1 becomes TdS plus VdP is equal to 0. That is equation number 5. Now let entropy is a function of pressure and temperature. Now let entropy is a function of pressure and temperature. Therefore, S is equal to function of pressure and temperature. ds is equal to ds by dp of t. ds by dp of t at dp is equal to ds by dou t of p dou t, which is equation number 6. Now substitute equation 6 in 5. Substitute equation 6 in 5. Then t of ds by dp of p dou p plus dou s by dou t of p dou t plus vdp is equal to 0. Therefore, t into dou s by dou p of t into dou p plus t into dou s by dou t of p into dou t plus vdp is equal to 0, which is equation number 7. Therefore, according to fourth Maxwell equation, Sherry. आपको this is clear now? So that here what we are taking equation 6, we know that. Now substitute equation 6 in 5 means we are getting equal to 0. Then t into dou s by dou p of multiplying t with both the terms. Then what we are getting t into dou s by dou p of t dou p plus t into dou s by dou t of p dou t plus vdp is equal to 0. T into dou s by dou p of t dou p plus t into dou s by dou t of p dou t plus vdp is equal to 0, which is equation number 7. According to fourth Maxwell equation, dou s by dou p of t is equal to minus dou v by dou t of p. And we know that t into dou s by dou t of, and we know that t into dou s by dou t of p is equal to dou q by dou t of p is equal to cp. Now substitute equation 8 in equation 7. Substitute equation 8 value in equation 7. Then minus t into dou v by dou t of p. Minus t into dou v by dou t of p dp is plus cp dt plus vdp is equal to 0. Then cp dt is equal to t into dou v by dou t of p dou p minus vdp. Then cp dt is equal to t into dou v by dou t of p minus p into dp. In both the terms, dp is common. Then dt is equal to what it is, 1 by cp into t into dou v by dou t of p minus p dou p. Then dou t is equal to ఏమవుతుంది 1 by cp t into dou v by dou t of t into dou v by dou t of p minus p. Therefore, dou t by dou p of h. Dou t by dou p of h is equal to 1 by cp into t into dou v by dou t of p minus p. 1 by cp into t into dou v by dou t of p minus p, which is equation number 9. Or mu jet is equal to dou t by the mu jet is the Joule-Thomson coefficient. Dou t by dou p of h is called Joule-Thomson coefficient. Joule-Thomson coefficient dou t by dou p of h is equal to mu j that equal to 1 by cp into t into dou v by dou t of p minus p. Therefore, mu j is Joule-Thomson coefficient. Mu j is Joule-Thomson coefficient. Dou t by dou p of h is negative. Dou t by dou p of h is negative. That equal to heating effect. Dou t by dou p of h is equal to negative. That is called heating effect. Dou t by dou p of h is equal to 0. Dou t by dou p of h is equal to 0. There is neither cooling nor heating. Okay, ma. Dou t by dou p of h is negative heating effect. Dou t by dou p of h is equal to 0 means there is neither cooling nor heating effect. Therefore, Joule-Thomson coefficient mu j for a perfect gas. For 1 mole of perfect gas, how to define that? For 1 mole of perfect gas, now we will give the derivation for that. Okay, here PV is equal to RT. PV is equal to RT on differentiating with respect to temperature at constant temperature. On differentiating with respect to temperature at constant pressure. P into dou V by dou T of P. P into dou V by dou T of P is equal to R. Dou T by dou T means 1. Then dou V by dou T of P is equal to dou V by dou T of P is equal to R by P, which is equation number 10. Substitute equation 10 in 9. Substitute equation 10 in 9. Then dou T by dou P of H is equal to dou T by dou P of H is equal to 1 by Cp into T into R by P. T into R by P minus B. Then dou T by dou P of H is equal to 1 by Cp into what it is R by P. R by P we are taking dou V by dou T of P means R by P. Then it becomes T into R by P minus B. That we are taken as B minus P. PV is equal to RT, B is equal to RT by P. No, instead of RT by P, now we are taken as V. Then V by B minus B means 0. 0 into something 0. Then dou T by dou P of H. Dou T by dou P of H is equal to 0, which is equation 11. Therefore, Joule Kelvin effect for a perfect gas. Joule Kelvin effect for a perfect gas is 0. Now, Joule Thomson coefficient for van der Waals. Joule Thomson coefficient for van der Waals gas. According to equation of van der Waals gas. According to equation of van der Waals gas. What is van der Waals equation, ma? Van der Waals equation is P plus A by V square. P plus A by V square into V minus B. P plus A by V square into V minus B is equal to RT. Now, on differentiating above equation with respect to temperature, on differentiating above equation with respect to temperature at constant pressure, with respect to temperature at constant pressure, P plus A by V square into dou V by dou T of P plus V minus B into minus 2A by V cube. V minus B into minus 2A by V cube into dou V by dou T of P is equal to R. Then what it is, ma? Dou differentiation of UV is equal to UV dash plus VU dash. Differentiation of UV is equal to UV dash plus VU dash. Then P plus A by V square minus 2A into V minus P by V cube into dV by dou T of P. In both the terms, dou V by dou T of P is common. The LHS terms we are taken that equal to R. Then finally, what it is, ma? Dou V by dou T of P is equal to R by P plus A by V square into minus 2A into V minus B by V cube. Therefore, R by RT by V minus B minus 2A into V minus B by V cube. Now, in both the terms, what it is, ma? P plus A by V square is equal to RT by V minus B. RT by V minus B. Now, you are substituting in that equation. You are getting final equation is like this. R into V minus B. Down V minus B is taken as upwards. R into V minus B by RT minus 2A into V minus B whole square by V cube. V minus B whole square by V cube. Okay. After that, continuation, I will show. Dou V by dou T of P. Dou V by dou T of P is equal to R into V minus B. R into V minus B by RT minus 2A by B. Dou V by dou T of P is equal to R into V minus B by RT minus 2A by RT minus 2A by B. On neglecting B square and 2VB in comparison with B square, we are getting the equation as 2 into TV by dt of P. T into dou V by dou T of P is equal to RT into V minus B. RT into V minus B by RT minus 2A by RT minus 2A by B. RT minus 2A by B. Then in both the terms, RT is common. Then V minus B by RT into V minus B by RT common means 1 minus 2A by 1 minus 2A by RTV. Then T into dou V by dou T of P. T into dou V by dou T of P is equal to P minus P into 1 minus 2A by 1 minus 2A by RTB whole power minus 1. Then T into dou V by dou T of P is equal to B minus B into that minus 1 take before. Then it is 1 plus 2A by 1 plus 2A by RTB, which is equation number 13. Therefore, dou T by dou P of H, dou T by dou P of H is equal to 1 by Cp into B minus B into 1 plus 2A by RTB minus B. Now, multiplying this equation and adding that 2. Then 1 by Cp into B minus B plus 2A by RT minus 2AB by RT. B minus B plus 2A by RT minus 2A by 2AB by RTB minus B. Then what it is, plus B minus B cancel. Then 2A by RT, are neglecting 2A by RTB term. Then we are getting dou T by dou P of H. Dou T by dou P of H is equal to 1 by Cp. Dou T by dou P of H is equal to 1 by Cp 2A by RT minus P. For the inversion temperature, dou T by dou P of H is equal to, for the inversion temperature, dou T by dou P of H is equal to 0 and T is equal to Ti. From equation 14, 1 by Cp is equal to 1 by Cp into 2A by RT, 1 by Cp into 2A by RTI minus B is equal to 0. Therefore, 2A by RTI minus B, 1 by Cp is not equal to 0, then means 2A by RTI minus B is equal to 0. From that, 2A by RTI is equal to B. 2A by RTI is equal to B, which is Ti is equal to, otherwise Ti is equal to 2A by RB, which is Ti is equal to 2A by RB, which is equation number 15. This is the inversion temperature. Is it clear, ma'am? Is it clear, ma'am? Is there any doubt? Joule-Thomson cooling effect. Joule-Thomson cooling effect is completed. Okay, Joule-Kelvin effect or Joule-Thomson effect. Joule-Thomson effect or Joule-Kelvin effect. Joule-Kelvin coefficient completed. Next, low temperature physics we will start in next class. Introduction. In this chapter, we will discuss the low temperature and its applications. Various methods of reducing low temperatures are endothermic mixing of substances, phase change processes, and expansion of gases, adiabatic demagnetization, phase transition. All these are there. Next class, we will discuss that. Okay, phase transition, and first order phase transition, first order phase change. So what are the processes we are getting here? Low temperature, expansion of gases, adiabatic demagnetization, and phase change process, endothermic mixing of substances. All these we are studying in particular low temperature physics. Here also forest plug experiment is there. First block completed till here. Total entropy, Maxwell equations, Joule function, Joule Kelvin. potentials, Maxwell equations, viscosity, fusion, diffusion, everything. Now we'll go for low temperature physics. Okay, is it clear? We'll discuss in next class low temperature physics and its applications, how it is getting low temperature and what is the Maxwell's distribution, Fermi-Dirac, Bose-Einstein, and all these we discuss in next class.